Yeah, actually, I would like to get started with that first picture. When you are developing for embedded systems, the thing is that you would like to have as a former engineer is the ability to have my hardware basically on my desktop. That is what I like to have. The reason is I can actually tinker with it, and I know it actually is working. But on the opposite side, when I have my colleagues saying, hey, Jeremy, I would like to actually have your latest version, then there is no way I can actually easily share that, let alone think about sharing it across basically the ocean to at least tell other co-workers that they can actually access that. I have my own setup, and it's very hard actually to share that. On the flip side, when you look at the cloud, this is something that is ubiquitous. I mean, there is infinite compute, and it's very easy to share. So the purpose of today's talk is to find out either a way we can actually combine both of them together, both of those worlds, to really make the best out of it. My name is Jeremy. My pronouns are he, him, and his. And please, I would like to try to solve that problem today. Let's get started. The very first thing we could think of is the answer to actually virtualize everything. If we were to virtualize our platform, then we can actually solve a lot of the problems. But then comes the question that I would like to highlight is, we look at virtualization as a balance between the time, the money, and the performance accuracy you want to reach with your virtualization model. The reason is, from an engineering perspective, you can spend a lot of time actually doing that virtualization, get the performance that you want. But from the business side, you may actually realize that you're going to spend too much time getting the accuracy that you're reaching, and therefore you will actually maybe miss the deadline that you had in mind. So that's something that we would like to try to define. How would you like to accelerate your hardware and software development with AWS? I want to walk you through that journey to go from the model basically to real ECU with curated partner that we have, solution guidance. The very first part comes when you're designing is you have access to a lot of tools. All of those tools typically would be installed on your desktop, and I have my own setup that I'm super happy is working very well. But my colleagues basically have their own setup that is working well, but the problem is sometimes they would actually collide. Now we do not even talk about the fact, yes, we are working with suppliers, and you will also work with customers. So for them to have the same environment, this is very hard. So how to solve that? You want to have a single platform for all of your tools, for your teams, your suppliers, and your customers, so that you actually make sure that everybody is actually using the exact same one, so there is nothing such as, oh, on my computer it actually is working, but it's not working on yours, and you're basically wasting your time doing it. I want to give you an example of what we call a virtual engineering experience. The very first thing you will actually do is you will log onto a portal, and this is the part that is actually very important. You have to put your own logins, I mean your usernames, and this will actually attach to all of the tools and the credentials. You should be able to have access to the Git repos and stuff like that. That means when I need to onboard new people, this is done basically in one day, something that typically will take weeks to be able to set up. Then I have access to a list of tools. So please, here is a sample of the tool and partner that we're working with. We're working with many more partners, but all of them in that case are RISC-V supported. Behind that, I will actually have access to my tool and do the work. So it's exactly the same experience as if I were to have everything installed on my own desktop. The only difference is because I go through that portal, I have the opportunity to make sure that everybody is actually using the same version. And when I'm making a change, everybody has access to that change as well. I told you that this was just an example, so we work with a lot of partners. So here, please look at our community. I would like to do one highlight. Yesterday, we did, for the very first time, a fun exercise. We actually said, okay, wouldn't it be interesting to be able to have people create their own design and do that in a workshop that actually lasts for only 2 hours, where there's only 1 hour and 30 minutes to do it. In a typical fashion, if you were to have to do it, there is no way you can do it. So we work with Chip Inventor. That is the first one that actually does cloud EDA very easy. And surprisingly, or actually should I say not surprisingly, it works seamlessly. And the way we've done it, actually I will give you some details afterwards, but that's why I wanted to highlight Chip Inventor on that. I want to take a step back and talk more about virtualization. I would like to actually, let's take a deeper dive into virtualization levels. I'm taking that slide from our friend at Synopsys that actually define different level of virtualization. If you're not familiar with it, if you look at your left-hand side, this is models. So those are very easy to actually emulate. And all the way to the right is the actual real hardware. From an engineering perspective, you wish you could be on the far right-hand side, because that's where you actually have your comfort zone. That's where you know that the performance is exactly as you expected. But the interesting part now is the further you go to the right, the harder it is to actually get to scale. The further you go to the right, when you go to a 4B, the more compute instant that task is actually going to be. So now that means the real time is actually going to be slower because it actually gets more complex. So you need to find that right balance. We are being asked several times, okay, what is the level you should actually be using? It actually completely depends on basically what is the goal of that specific team that is working on it. So in the same company, for the same project, you will actually be using several levels depending on the need that they have. And that's what matters the most. In your mind, you should actually try the very best to stay to the left as much as possible and try to define by requirements the reason you actually need to move to the right. I want to make a highlight here, very specific at the very bottom. You see that this is coming from Synopsys, and we're actually observing the same thing. The observation is 90% of hill tests, hardware in the loop testing, can be done in SEAL. And why this is important, the majority of hill, you cannot scale that easily. Once you actually purchase the hardware, you need the time to procure it, you need the power, the cooling, and you actually need to have the space. And this is actually very hard to maintain. And most of the time, you have some hardware failure and you have to deal with them. So you're actually wasting a lot of time trying to set up that hill farm, which is not yielding the result that you want. When you go to the SEAL side, this is much easier to actually reproduce and to scale to a much bigger, scale. So that's why we actually want to see how we can actually marry those. As a rule of thumb, when it comes to virtualization, enables functional development and testing. That actually is working very great. Performance accuracy can be rich, but there is a return on investment that needs to be analyzed to figure out, okay, how far do you want to go into that virtualization and accuracy. If you're doing ARM, then you can actually run native code basically on AWS Graviton that actually is Graviton-based. Being at RISC-V, the question is, what about RISC-V? I started the talk by telling you that we wish we would have access to actually embedded hardware, and how can we actually get the parity, because that's what we ultimately want to have, either way. When we look at the RISC-V community, we see that emulation is being used. That is actually awesome, but we also see a lot of the community starting everything with an FPGA. The reason they use that FPGA is for obvious reason, that basically you get better accuracy and you can actually get to very close to what the ASIC will actually look like. But the problem now is I have my dev board. This is hard to procure. This is hard to share with my customers. If only there was a way to have that access at scale. And the answer is yes. If you look on AWS, we have our F2 instances that are FPGA-based. You can look at it. It's the AMD Vertex UltraScale. I'm not going to try to read the exact spec of it. If there's something to remember from that presentation is, because we have FPGA available at scale, everything that I said that we could actually do with embedded with the board on your desk, and the benefit of the cloud, now we can marry those two together. Let's have a deeper look. Let's start from the left-hand side. We actually have prepackaged some tools, so VDIS, Vivado, OpenCL, what we call a hardware development kit. This is something that contains everything you need to do development for the FPGA. In the middle, the custom logic is your part. So you put your IP into this. And as a result of it, you get what we call an AFI, an Amazon FPGA image. For the one familiar with AWS, you typically use an AMI, which is Amazon Machine Image. An AFI is the exact same thing. The only difference is it actually runs on the FPGA. That actually means I can easily do a snapshot. I can easily share that with my colleagues. I can easily share that with my customers and my suppliers. I can even put that on the marketplace. And there, I'd like to double-click on that one. When I put that IP on the marketplace, it is IP protected. So that actually means if I'm a RISC-V IP developer, and I want to be able to reach out easily to my customers, and at the end of a presentation be like, okay, you want to try out that? Oh, actually, here's the link, and in one click, they actually are ready to go. You get to decide how you actually want to monetize that, if you want to basically provide it for free, or if you actually want to charge some fees, or you can also do bring your license type of perspective. We see it as a moment that actually is changing the RISC-V community, because we enable even smaller companies to be able to reach to a broader audience, to be able to have the exact same IP that they are developing in the hand of the customers without having the need to have field application engineers giving a call saying, oh, are you using exactly that FPGA board that we told you to buy? Oh, that's the revision B, and I'm sorry, this actually is not working there. Oh, you actually, there's an issue basically with that specific hardware. Please change it. Here, you get the full control of the experience of your customers. The reason I have at the bottom the F2 is that from a customer perspective, they go on the AWS Marketplace portal, they can actually get to choose your IP, and then they will flash it onto the FPGA, and they get to access it, and basically you can easily have a workflow with that. I was mentioning Chip Inventor earlier. That's exactly what was happening yesterday during the workshop. The RV35i was just used because it was a small workshop to get people started, and that's actually how it was done behind the scene. We may actually think, okay, are we done now, Jeremy? I mean, at the end of the day, I told you that, yes, we can actually use virtualization. We can use those FPGAs to be very close. But there was one thing, which was 90% of testing can be done on seal. Now there's still the remaining part where you actually have to have access to that specific hardware. I wanted to let you know that we can also cover for that. This setup on the left-hand side where you see the AWS logo is using AWS Outpost. What are AWS Outposts? Those are the exact same server that we have in our data centers that we can actually provide to our customers so that they can have that in their lab. Why this is important? You actually have the one for x86, the one on ARM, and then the other thing is you can connect it to real hardware. In that case, this was connected to an Infineon Tri-Core board, but the idea is that you can connect it to your own board. So may that be actually that FPGA where you have something very specific, you want to test a specific IO, you can do it. Why does it matter? All of the tools and your engineers who actually know how to leverage AWS now can actually use the exact same one, but on-prem. And the other thing that is very important is you can provide remote access to anyone that actually is, I mean, you want to. That actually means it can be your own coworkers, but it can also be your suppliers. When you have something that is not working on the board, when they actually provide, let's say, a bootloader, and it actually doesn't work for your board, you can say, hey, please get access to this, as opposed to have someone to fly and basically try to fix that board. Or you can also provide access to your customers. And the beauty of that system is it's in a secure manner. In that setup, we actually have one board, but obviously that scales to as many boards as you would wish you have. And they can get that private access. They do the work that they need. And then when they're done with it, you can actually remove that access and have somebody else actually use it. That's why we look at it as basically it's all virtualization in one setup. I'm not going to go into the details of all of the options that you have, but if there's something to remember is there's not just one way to actually do that connection. On the right-hand side, you actually see whatever you will actually have on-prem. So you actually have your Hill farm, and then you have either the outpost that can be connected, or depending on your connection, if you have what we call AWS Direct Connect, that is actually a fast highway, let's say, with guaranteed basically latency and bandwidth to AWS. You could directly attach an EC2 instance, a compute instance that's running on AWS. That compute instance can actually be an FPGA. That FPGA could be the RISC-V that we were talking about before. And then over Ethernet, now it can communicate with real hardware you have inside your lab. If you want to manage this, we actually have many ways, but one of them that I'm particularly interested in too is actually EKS hybrid node that enables you to actually do the orchestration of your workload. So now if you have basically your emulation plus a lot of your work can actually be done on FPGA that are hosted onto AWS, plus then the extension with the actual real hardware with one single pane basically of control. There's just one way to control all of that, and all of the orchestration layer is actually done by Kubernetes. That we think is changing the way to do development. The main reason is now you can actually start to focus on developing the IP, but all of the underlying infrastructure is something that actually is being taken care of by actually managed services. We started our journey with actually the cloud and the thunderstorm, saying, oh, there's a difference between embedded and the cloud. And actually what I would like to say is at the end of that talk is I hope that I've actually managed to show you that there are actually ways to reconcile both, to actually show that they can actually benefit from one another. And at the end of the day, we can actually take advantage of both solutions. I have a call to action for you. If you are developing IP for RISC-V, I will highly encourage you to look at the workshop that we have, where you can actually get started to understand how you can actually work with FPGAs on AWS. And then there's also a specific section that says how you can actually list your IP onto the marketplace and start to monetize it, or basically provide it for free for the community if you want to. There's also a solution guidance to do scaling of EDA on AWS. And at the bottom right, you can actually see that actually is an offering on the marketplace, which has, it's what we call an AMI, which has everything you need to basically develop on FPGA. It's just as simple as that. So what we really want to convey as a message as opposed to actually start with, oh, you have to download this, you have to install that, and everything should be compatible, and we don't really know if the computer environment is going to be good. We can make sure that here you can actually control everything. We have a lab in Santa Clara where we're hosting several meetups. The QR code is actually here for the meetup group. So if you're interested to dive deeper and actually spend more time to actually do some tinkering, we're more than welcome to have you join that. And also if you want to demo your own technology, we'd be happy to actually have it there. If you have any questions, we will not take them now. But the idea is that here's my LinkedIn information. I would like to thank you very much for your time, and I hope that was interesting to you. Thank you so much.